Hello and welcome again to my Physics Online video lecture series. Today's video, I'm going to be kind of continuing my previous discussion of electromagnetic waves. Maybe introducing electromagnetic waves as sort of the immediate consequence of Maxwell's equations. I kind of did that in my previous video discussing Maxwell's equations, but electromagnetic waves being one of the principal predictions of that, and certainly the one that was historically most well known as the tested prediction via the Hertz experiments. So today's video, I'm just trying to set up. These are the sort of equations that describe electromagnetic waves. Of course, this is going to be an algebra-based discussion. I'm not going to try to set up like the wave equation or anything like that for you all. That belongs more to a calculus-based physics course. But I will maybe describe electromagnetic waves a little bit, talk a little bit about the essentially what is the E field doing, what is the B field doing, and maybe kind of go from there. So you'll recall, and I'm not going to write anything for this particular recall, but you will recall that I previously discussed Maxwell's equations, basically Gauss's law for electric fields, Gauss's law for magnetic fields, as well as the Ampere's law and Maxwell's sort of modification to it, and Faraday's law, and how in particular those last two give rise to the idea that if you change an electric field, then you can produce a magnetic field, and if you change a magnetic field, you can produce an electric field, and that doing this is essentially accomplished by accelerating charges. So what does that actually look like, or how might we describe those waves? Well, your electric field is produced, simply by a charge in general. So if I have like a positive charge here, I expect my electric field to basically look something like this little sketch that I'm making. Field lines sort of radiate outward from it in all directions. And now, I could ask, what would happen if this charge moves a little bit? Well, the answer is, if the charge moves, then all these field lines have to somehow shift as well. Like, if the charge is here, then this is where my field lines are. If the charge is down here, then I expect the same set of field lines, but kind of displaced a little bit. And when we discuss these things, we do it as if this thing is static. So the charge is just kind of sitting there. But what would happen if I actually literally had this charge move from this point to another point? So what if I actually moved this charge from here down to here? Well, if I moved it suddenly and then just kind of let it sit for a while, then after a while the field lines would basically just kind of radiate out from this point like so. Okay, so I just kind of have a new set of field lines. And yes, the electric field values would be somewhat different at each point in space. I think if you were to measure the field, say like right here before and after, you'd find that the field is somewhat weaker, but in the same direction. If you were to measure the field, say like right here, both before and after, then the field is perhaps the same magnitude in both cases, but opposite directions. Once I've moved it, the field is actually upward, but before having moved it, it's downward. So either way, we could say, yeah, it's changed. If I were to measure the field strength somewhere like over here, though, that would have a fairly dramatic change. Like initially, the field should be pointing this way. Finally, the field maybe is pointing more or less this way. It's weaker and the direction has changed. So when does that change occur? Well, as it turns out, it's not instantaneous. It turns out that it takes some amount of time for this information about this particle being moved from here to here to propagate to this third point some distance away. How much time does it take for this local field to change? Well, it depends upon the distance that this is from our two particles, if you will, and it depends upon the speed at which the information propagates. Well, that speed of propagation, we could call it speed of E-field information propagation, is, as it turns out, c, where c is approximately 3, it's actually a little bit less than 3, times 10 to the 8 meters per second. Okay, so let's say that I've moved this thing from here to here. Let's say that that happens in a millisecond. And let's say that a signal traveling from here to this point takes another 5 milliseconds to arrive at this location. Well, essentially, it would take 1 millisecond plus 5 milliseconds from, maybe this is time 0, this is time 1 millisecond. Take that long for the field at this location here to have shifted from this to this. And that shift doesn't just kind of 5 milliseconds later power this way. The shift is it is rotating and also decreasing until it reaches this final stage. Well, how is it doing that? Essentially, the electric field lines are moving as this moves, but they're moving with a delay of whatever the distance is over c time. Okay, so that delay, takes a little while to occur. Now imagine, instead of just moving this particle from here to here, imagine if I were to have some way of making the particle suddenly move, kind of up, down, up, down, up, down. Maybe I even oscillate it as would happen in an AC signal. Well, that basically means that my electric fields are continually shifting in their direction at each point in space. And yes, there's some propagation time for that to occur, but that propagation time doesn't change the fact that they are shifting. And once I've got the signal sort of arriving at this point right here, thereafter, I kind of expect the field to begin oscillating, delayed with, but on a similar period to the oscillation of this source. Well, that just is the same description that we use to describe mechanical waves. In a mechanical wave, I have a disturbance. Let's say I have like a rope. I have a disturbance, so maybe I grab one end of the rope and move my hand up and down to move that piece of the rope up and down. Well, sometime later, the segment over here starts to vibrate up and down as well, and the period of vibration for this and for this end up being equal. The magnitude may not be the same. It may be that this is vibrating like this and this is vibrating a bigger distance. So we're doing something like this. But once they've sort of like synced up, they're synced up. And there may be another piece here that is counter vibrating with this at the same frequency, and so on. There's sort of like a set phase between one point and the next point on my rope. Well, the same is true with these electromagnetic waves. These are electromagnetic waves. Basically, I'm moving this up and down. It's changing my electric field everywhere in space, and that's causing me to have essentially like a wave. Well, at least it's causing me to have an electric field wave. But going back to our little recall thing, what happens if you change an electric field? Well, according to the Ampere's law, you get a magnetic field. You induce a magnetic field. And it turns out that that magnetic field will be also sinusoidally changing, which in turn allows us to sustain a changing electric field, such that even if I just simply move this from here to here, I should have a changing E field, which produces a B field, which induces an E field, and that allows a propagation of some signal out into space, even though this thing has long since stopped moving. And that is electromagnetic radiation. So the equations that ultimately kind of describe the simple electric field and simple magnetic field look like this. The E field has some maximum value, we could call it E naught, times the sine of essentially like a wave vector of some sort, dotted with displacement from wherever we've marked our origin. And then depending on whether you want the wave moving left or right, it's either minus or plus omega t. In other words, it looks very similar to, compared to y is equal to y max or y naught sine k dot x minus or plus omega t. Okay, that was just the equation for mechanical waves. And it turns out that along with this E field wave, I get my B field wave, which looks like B naught sine k dot x minus or plus omega t. Okay, so these are my electromagnetic waves. There are some parameters that can be discussed here, but I think that's for another video. It's worth noting that since these are sinusoidal, we can reduce this, by the way, for one dimension. The 1D case, I would simply have E is equal to E naught sine k x. Let's say it's moving to the right, so we'd say like minus omega t, and B therefore must be B naught sine kx minus omega t. Either way, there's a nice connection, which is that the k and the omega over k, is equal to the speed at which the thing propagates, which is c, and E over B is equal to c. So the two fields' magnitudes are related at all times for a given point in space by the same propagation speed c that the wave is propagating at. Now, in a future video, I will discuss these parameters further, but I think that's good for today.